Okay, this tutorial is going to cover some basic techniques in Karamba for analyzing structural skeletons and analyzing kind of shell structures or vault-like structures. So I'm starting in this definition with tower geometry from a previous tutorial. And so this tower geometry is the one that's just based on a grid of subdivided points from an original surface. So that's just a simple lofted surface, grid of points, and then a series of interconnected lines. So we have a series of horizontals, a series of verticals, and a series of kind of twisted verticals. Okay, so and the reason I mention that is because when we do our definition, basically we're just going to feed Karamba a series of lines. I think you will also want to make sure that you have these as individual line segments, meaning not curves. So you want them to be straight lines, and you want them to also probably be exploded. So once you have kind of a definition for a geometry here, and it doesn't have to be a tower, it can be any kind of structural frame, we're going to go ahead and load up Karamba somewhere in here. Okay. So you can check whether your license is working. So there's a free version of Karamba that you can get, and it has a limit of a certain number of components. I think it's 50. So for example, if we'll just go ahead and do this step right now. So I'll put all these components together into one. They're all our lines together. We could distinguish them if we wanted to give them different kinds of properties. For this, we'll just use one, put them all in one component. And then I'm also going to explode those curves. Because remember, they're polylines, so we want them to have individual segments. So we have about 500 lines here. So that would be obviously more components than what the free version would handle. I believe that our computer labs will have a version of Karamba that you can use. Or you can also buy a license. They're perpetual, meaning they last forever, and they're not that expensive, 50 euros. But it takes a day or two for the process to be complete. But anyway, it is a really useful software. But so I'm going to go ahead and start setting up my Karamba definition here. Now let's see. There's one other thing. So first so we have all these components as lines. And we're going to go ahead and we're going to start by turning those into some kind of structural member in Karamba here. So let's see, if we go to model here on our Karamba tab, we can go line to beam. So this is one method of creating a kind of a beam or a structural component. Obviously, there's a few others depending on what type of data you want to use. But we have lines, so we're going to use our line to beam component. I find it useful to just to start with this component and work my way backwards. So I'm going to go ahead and plug those in. I may actually also flatten this here. Okay. All right. And with most of the Karamba components, you can also expand some more options down there, just so you know. Now we're going to also, then we're going to work our way backwards from the inputs of this definition. So now it's going to ask us what kind of cross-section we want to select for our beams. So it knows what lines to turn into beams, and it wants to know our cross-section. So under the cross-section menu, I'll select this one, cross-section. There's a couple different ways you can do this, actually. Cross-section selector, that might be, I think that's actually easier. And we'll go ahead and plug that in. And then I believe this thing also needs an input as well, where it says cross-section. So I'm going to go ahead my cross-section tab and go to cross-section range selector. Oh yeah, so what we're actually going to do in this definition, which will be useful, is we're gonna kind of supply a range of possible structural cross-sections to our definition, and we're going to allow the analysis to select to kind of size the members itself. So we could just plug in a single size and kind of look at the forces. But this, in a way, gives us more information and helps us understand our model a little bit better. And so I'll go ahead and plug this in as well. And under country, we can set some of these things. We'll do an I-beam. And we'll do we can just do all, leave that on all. Okay, and then the only other thing we want to set is the material. We want to also give this a particular material. And so I'll go to the material tab and go to material select. And then we can choose steel, whatever kind of grade we want. Again, these are things you'd be more concerned with if you were really kind of doing engineering, but I don't know. I honestly don't know. We'll just pick one. All right, so plug that into material. All right. So I believe that's kind of all we do to set the cross sections up. So that's kind of applied a cross section there. And then the other thing we need to apply, just like in Kangaroo, actually, you're going to apply a load. So we can use Karamba actually to analyze all different types of loads. We can use it to analyze like a dead load, like gravity. We can use it to analyze like a wind load, so kind of a horizontal load. In this case, we're going to do gravity. So we'll go to, up here at the top, we'll go to load. Let's click that. Oops. All right. And we'll leave it set to the default, which is gravity. And then it's going to ask us for a vector. It's already set to -1 by default. But we could, we could set that to a slightly different direction if we wanted to, or we could give it kind of a greater amplitude if we wanted to. But for now, we'll just leave that alone. So those are our loads. And then the other thing it wants to know is what are our supports? Where are we actually resolving some of the forces in our structure? So where is that? So we're looking for, okay, under model, down here where it says support. And support just needs to know some points, some nodes where we're constraining our model. In order to find that, I'm going to go back to my original definition here. And this is kind of a tower structure, so I'm just going to use basically all the points around the bottom edge of my shape there. So I'm going to go to where my horizontal lines are. And I think those are also, I'll also get another curve component. Okay. And then I'll go ahead and flatten that. So everything's in one list. Oops. And then I'll also go ahead and plug in a list item, and that'll give me just my bottom horizontal cross section. And now I just need to return all the points basically along that outline. There's a couple ways I can just go explode, or actually, control points is the better option. Here we go, control points. So if I plug that polyline into this component, it should give me all of the control points that define it. Now, one thing I'll say you have to watch out for is, because this is a closed polyline, it's going to give us 2 points in one spot at the start and the end of that cross section. So at the start and end, it's giving us basically a duplicate point. Because it starts somewhere, goes around, and ends somewhere, right? So we need to, and that will confuse Karamba. So we need to get rid of one of those points, either the very first or the very last point in this list. I'm going to go ahead and get a component called call index. I'll set the index to 0, the integer. So it's going to call the item at index 0, remove item at index 0. Put that into my points. And then you can see I still have every point in there, but I have one fewer in my list. So I removed the duplicate. There's like a call duplicate, I believe. Component now in Grasshopper, you could use that as well. That would have a similar effect. Yeah, it did the same thing. Okay, so those are our points. And it also wants to know a plane orientation. So when we plug these points in, and we'll plug them into where it says position, if we expand where it says conditions, we're going to get 6 different options. So the T stands for translation. The R stands for rotation. What that means is that at each of these points, we're going to tell it, at that point, we're going to constrain it in terms of movement in certain directions, right? We know that this point can't slide or shift, right? But we might not constrain it in terms of rotation, right? If we had something like a pin connection, that can obviously rotate in some dimensions and not in others, right? So we can constrain the kind of direction of the rotation. And that's why we want to be able to set a plane, right? So for example, if we had pin connections that sort of followed the orientation of our curve there, we would have to set an individual plane for each of those to get that rotation direction right. In our case, we're just going to leave this empty because we just want to leave the, we don't have any special conditions where we're going to constrain it. We'll just constrain everything. And by default, I think it'll go to the world XY plane, so we don't have to set anything for that, but just so you know what that does. Okay, so now we kind of have everything, all the parts we need. And then we're going to do something called assemble. We're going to kind of put our model together into the components that perform the analysis. So I'll get this component called assemble under model. And then we should be able to kind of follow the name. So we'll plug elements into elements. We'll plug loads into loads. We'll plug supports into supports. And it'll actually give us an output there, which is the mass of the structure. It'll give us some information, but obviously it's not performing. So we've put like all our components of our analysis together, but we haven't actually done any kind of analysis yet. So the next component we would want to do, and this was what I was referring to earlier, we're going to use this component called optimize cross section. And let's see here. Remember if it's in here or if it's under algorithms, optimize cross section. We'll go ahead and plug that into our model. Plug the cross sections in back here. Oh, sorry, actually, into the cross section selector, range selector. Because again, we want to give it like a range of possible cross sections to choose from. All right, and so that's going to now apply a structural element to each member that we've input into our definition. And finally, what we need to do is actually add some more components that allow us to see what this thing is, what kind of information this thing is producing. So if we go to, I think it's actually under results, model view. And we're going to plug in our model to this guy. So right away, and let me unpreview some other stuff back here. You can see it's spitting out a definition where we can see our deformation. We can see our load vector. We can see our constraints that are applied to the supports. And I think if we expand where it says display scales, set to 50 by default, we can actually look at how this tower would deform under this load, in what directions it's weak. So we turn that on, it'll actually give us information about what kind of forces are moving through our supports. Yeah, so we can turn all these things on and off. All right. And that's giving us kind of an analysis of our model. So we can also we can start to bake these things. And we can also look at certain data that tells us, what the kind of performance is, how well our structure is performing. But there's another component that actually allows us to see the beams that it's selected from our list of cross sections. If I go to results and I go to beam view, and I'll plug the output of my model view into this one. And I'll unpreview this. And so there you can see it actually is modeling like a little I-beam for each connector. And I think if so if I go to render settings under this guy, we can actually start to see, and it's kind of hard to see because of the edges, but we can start to see sort of a color analysis of where our forces are in our structure. Which ones are doing the most work, which ones are doing the least, that kind of thing. And of course, what's really interesting about that is that when we vary our original definition, the geometry of our tower, this is my twist, zoom out a little bit. So we can kind of see how well the structure performs based on the shape. So we can start to see those variations in forces. I think if we can a little fewer. I wonder if we can, maybe if we turn up the loads, we can kind of get it to. So we'll apply a vector to our load, give it a number. I apply like a larger vector, there we go. Let's see. So there you begin to see like which pieces are thicker, which are thinner, which ones are in tension, which ones are in compression. And then if we like, I think what I actually found with this one is you twist it in a certain direction, it performs better. You can see there, it's quite a number of really thick lines. And if we twist it in the other direction, there's not as many. So based on the geometry we modeled, a certain directionality to the twist is more appropriate. You can see it also, sort of attenuates. The lines are thicker at the bottom, much thinner at the top. So that actually gives us kind of a mix between a parametrically generated structure in a structural form, and of course we could plug that into Galapagos too and optimize for you know, certain size members or certain you know, limitation of force, that kind of thing. So that video, that's going to conclude this video on structural form finding for skeletal structures. And in the next video, I'll cover the beams. I'm sorry, the shells. All right.